Hello, my name is Jon Wakefield. I'm a professor at the University of Washington in the Department of Statistics and Biostatistics, and this is the third of a series of lectures that I'm going to give on spatial models for survey data, the general theme being Bayesian subnational estimation. So this is the overview of where we're going in today's lecture. So I'm going to start by motivating the problem we're trying to solve in the methods I'm going to describe. I'll first describe traditional methods for small error estimation. Then I'll talk about smooth direct modeling, which is a particular approach to modeling, before talking about space-time modeling of under 5 mortality. That's going to be an overarching aim of this talk, how to estimate under 5 mortality subnationally in a low and middle income countries context. And so to do that, we need to learn a bit about survival models. Then the next section will be on an alternative approach to smooth direct modeling, cluster level modeling, and I'll end with a discussion. So, as I just said, we're interested in examining subnational variation in health and demographic indicators across some study region. And so this can be achieved by what's known as prevalence mapping. And that's the aim of that endeavor, is to produce continuous prevalence surfaces or area level maps. And what we're going to take as our aim is obtaining area level estimates. And the idea there is that we can target resources and examine progress towards goals at those area levels. And so this is a classic example of what's known as small area estimation. And just to introduce some terminology, small area estimation is what's called in the survey sampling literature domain estimation. And small here, just to emphasize, refers to the fact that we're typically trying to base our inference on small numbers of samples from a typically, or sometimes there can be small samples in areas, and in the limit no samples in an area. So just to get some notation straight, so I'm going to assume we have n disjoint and exhaustive areas in some study region. So that's a partition of the study region, and I is going to index those areas. So they're the target areas we'd like to make inference about. So as a concrete example, suppose we're interested in looking at a binary outcome. So I'm going to let yik be a Bernoulli random or Bernoulli variable or a 0-1 variable, Bernoulli in a model-based framework. And so we're going to, that's indexed by I and K. So I is the area, as I just said. K is people within those areas. And so there are capital Ni people in area Ni, in area I. And then based on the samples that we collect in the areas, then there's typically a couple of things we might be interested in. The total of those binary variables. So that's just the sum over all the people in those areas, or the prevalence. So if we divide the total by the population size, then we get the prevalence. We're going to focus mostly on the latter. So the classic text on small error estimation is Rao and Molina. That's not the easiest book to read, but it's certainly in terms of traditional methods, it's very encyclopedic, and it's relatively recent. There's some material on spatial smoothing models, but it's not some of the more modern approaches to spatial smoothing. A paper-length review is given by Pfefferman. That's a very nice paper, which is a nice condensation of a lot of the material that's been, or the current state of affairs in 2013. Again, there's not a lot on spatial modeling, but there is some very nice explanations for different traditional small area estimation techniques. And in the literature on small error estimation, there's an important distinction between direct estimation and indirect estimation. In direct estimation, we only use data from the area in which we're trying to obtain the estimate, whereas indirect estimation can use data from other areas to produce. So the totality of data can try and produce more accurate or precise estimates in the area we're interested in. So as an overview of this lecture, I'm first going to talk about traditional small area techniques, and then move to looking at approaches which we'll describe in lecture 2, so spatial and space-time models. But now, in that lecture, the second lecture that I gave, I talked about spatial models for data which were collected usually via simple random samples. So now we're going to see how we can incorporate the design in our spatial modeling. And there's 2 ways we're going to do that. One is through an approach that's called the smooth direct method. So that's basically going to take our weighted estimators, which I talked about in the first lecture I gave, and then smooths them over space and or time. And then the cluster-specific model is actually going to model at the level of the cluster. So if you remember the context here, we're usually dealing with household surveys which are gathered under a stratified cluster design. And so we need to acknowledge both the stratification and the clustering in general. And so we're going to specify models at the cluster level, and then we're going to aggregate those up to the area level. And the way we're going to model the cluster level prevalences is via discrete and continuous spatial models. So I'll describe both of those approaches, the discrete one in more detail. And along the way, we're going to talk about discrete hazards modeling because that's important for this overarching goal, which is to estimate under 5 mortality. So again, the same notation. So YIK is the response in area I from unit K. And now K is a member of some set SI. That is the set of samples that were gathered. So referring back to that first lecture, in the design-based view of the world, the Ys are not random, but what is random is the people who we selected. So the Ys are a bunch of fixed numbers which are out there, which we're just going to treat as fixed constants. The randomness is going to be introduced through the sample, whichever of those units we sample. And then along with each of these, the responses that the people we sample will give responses of the variable of interest. And then we'll also have an associated design weight, which if you remember is 1 over the probability of selection. And under the design-based approach to inference, we saw that a very nice estimator, an estimator with very good properties, is this weighted estimator. So for a prevalence, we just simply take the weighted average of those observed responses. So we're summing over the people who were selected, and then we weight them via these design weights. And then given that estimator, we can estimate a variance which is appropriate for the design. So we can either do that analytically, so there are certain formulas, some of which I spoke about in that first lecture, or we can do it through resampling techniques such as the jackknife. Then once we have the estimate and then the variance, then we can say asymptotically, so if we gather if that small ni is the number of samples, so we assume there's little ni samples gathered, then if that's not too small, then an approximation to the sampling distribution of the estimator of the prevalence, so under repeated sampling, so taking different individuals and a repeat sampling scenario, that estimator, which we've defined in the middle there, is going to look like a normal random variable centered about the true value, and then with variance given by the design-based variance which we estimate. And so the simplest approach to examining subnational variation is just to simply map those estimates. So on the right here, we'll see I've done that this is actually looking at U5MR over a particular 5-year period, sorry, I should say 2010 to 2014. And so we see here darker colors are higher rates of under 5 mortality across these areas in Ecuador, and with the yellows being closer to 0. And the hatching there reflects uncertainty. So denser hatching means there's more uncertainty associated with the estimate. So for example, here, this area has got quite a lot of uncertainty associated with it. To assess the uncertainty in general, we can map some measure of uncertainty, such as the width of a confidence interval or an asymptotic confidence interval based on that distribution on the previous page. So this approach, if you're only interested in perhaps larger areas and you have bigger samples, then this may be totally this may be the only thing you do, because you've got acceptable levels of variability just by doing this weighted approach. But if we try to drill down to lower levels, or if we're trying to do it in finer timescales, then often we won't have enough samples to get reliable to get variances of an acceptable size. So we need to do some form of smoothing to supplement these estimates in order to get the estimates with a reasonable width for credible intervals. I'm going to just talk now about 3 estimators that have been suggested in this traditional small area literature before we move to more models that are more familiar from a space-time setting. So this so-called synthetic estimator fits a model. So suppose we have some covariates measured in our areas. And so what we're going to do, this equation, this B hat, so this B hat is an estimator of it's basically a weighted least squares estimator of the association between our response Y and our covariates X. So we've got our covariates here, so it's the usual formula that we're, or perhaps not quite the formula that people are familiar with because we have these weights in here, but it's basically a weighted least squares estimator where we're fitting the model across this linear model, we're fitting it across the whole of the sample, all of the samples, so over all n areas and over all the sampled individuals in those areas. Now notice up here, an important point is we're actually applying this model, we're taking the covariates for all of the individuals. So we're assuming that there's some sampling frame, say, or there is a, in the sampling frame we know, so if we had, say, gender in this model, we knew the gender crossed with age or something like that. So we know all the covariates on the complete population, so not only the people we sample, but everybody else, because we have an NI here. So we're basically applying this model to everybody, the covariates from everybody in the population of area I. And then we are just, so this is giving us the mean, and then we're just dividing by NI to give us the proportion, or the average. So that's the point I'm making here. And so an obvious observation here is that this model is assuming that the reassociation between the covariates and the response is the same across all areas. So that may or may not be appropriate. In general, it won't be appropriate. So this is an example of what's called an indirect estimator because we're using information from all of the areas to inform on one particular area. The B hat here has been estimated from all of the data, and that's just being used here to estimate the mean for area I. So a nice thing about this estimator is that it's got very high precision. Because we're using all of the data to get this regression equation, the regression estimates, those regression estimates will typically have low variance, so this will have low variance also. But unfortunately, there's a possibility of large bias because of this assumption of a common model across all areas. So that leads to this so-called survey regression estimator. And so this deals with the bias by trying to estimate it and then adjusting the previous estimator. So here's what we had previously. Here's the synthetic estimator. But now we estimate the residuals here, so the difference between the YIK and the fitted values. We weight those residuals to, so that if you think about the interpretation of the weights as the number of people that unit K within area I represents, then this is weighting this up to the full population, and then we divide by NI because this is giving us like a population residual in area I. And if we rewrite that, we have this quite nice form that says it's the Horvitz-Thompson estimator, so the obvious weighted estimator we saw previously. But now we're adjusting it via this regression equation. So we're basically estimating, using the samples to estimate the average of the covariate in the area. We know the true covariate mean in the area. So the difference between here is in some sense how far off our so if we got quote unquote a good sample, these two estimates will be close and this estimate will be good. But if we get a poor sample here, then in the sense that the estimate of the mean is far from the true mean, which is known here in the population, then we have to adjust the estimator because, of course, we're assuming there's an association between the x and the y. So if there is an association, then we know the direction. If this estimate is off in the x space, we can adjust it to move it back into y, the response space. Now, unfortunately, so this is very nice, this estimator in a certain sense. It's very appealing, it's intuitive, but the variance now is of order 1 over little ni. So it depends on the number of samples you have in area I. So the areas with small samples are going to have very unreliable estimates, whereas the survey regression estimator is going to be reliable in areas with large ni. So the obvious thing to do here is to consider instead a composite estimator, which takes a weighted combination of the synthetic estimator and the survey regression estimator, and then weights them via some number between 0 and 1. So an area-specific weighting factor. So it's trying to balance the bias of the synthetic estimator with the instability of the direct estimator. And there's various ways that are described for estimating this delta I in a design-based framework, but we're going to proceed in a different route, And so Bayesian estimators are often weighted estimators between some kind of global and some kind of local trends. And so that's what we're going to do, but we're going to do that under a full model-based approach. So the first approach we're going to talk about is going to start with a very kind of incredible paper that came out a long time ago now, 40 years ago, which suggested a very appealing hierarchical model. So again, we're going to take pi hat to be the weighted estimator of some prevalence. And then we're going to take the logit of that to take it on, put it onto the whole of the real line. And then we're going to take as data this estimator of the logit. So rather than consider a model for the actual observations yik, we're going to assume that all the information about those observations and the weighting scheme can be succinctly described by the asymptotic distribution of this weighted estimator. So this is going to take the place of our sampling model or our likelihood. So all the uncertainty about the estimator is assumed to be summarized there, and then where we have this known variance. But then we're going to smooth. So then we're going to say, okay, this estimator, there's some overall level across the whole study region. Then we could model with covariates if we wanted. But then we're going to assume that there's some area-specific perturbations. So some, we're not going to, the synthetic estimator was similar to this in the sense it had a regression model, but now we're going to allow some adjustment from that regression. So the hope is we'll pick up these major trends via the covariates, and then we can do area-specific adjustments via these random effects EI, which in the original model were assumed, in the original Fay-Herriot model were assumed to be IID. So this is very appealing because the design is accounted for in this distribution, but then we're using some kind of smoothing here to trying to alleviate small sample problems. And there's an obvious extension here to spatial random effects. So here, again, to repeat, here's the data, feature I hat, and this sampling model. And then we now add in, so it's the same as the model on the previous page, except now we've added in SI, and I'm going to, again, assume these, as I did in the last lecture, talk about these S1 to Sn, these area-specific spatial random effects as arising from some ICAR model with an unknown smoothing parameter sigma squared S. So this is an area level as opposed to a unit level. So later on, we'll look at actually, you can have a unit level model or we can have a cluster level model. This is an area level model. And then these papers here use this model in the space-time context. And we're going to look at the space-time version of this soon. I just want to give you a quick illustration of this model, actually from a paper which came out earlier this year, looking at estimating HIV prevalence across districts of South Africa. So again, it was based on household survey data, and they used a number of covariates. So there's a number of covariates here, so important ones being things like the prevalence estimates from antenatal clinics. So that's a particular population that you're examining, so pregnant women, and so the HIV prevalence is different in that population than the general population, but you'd expect them to be some association. So you try and leverage that within the regression model. And then there's a number of other variables that are used here as well. And then on top, they didn't use an ICAR model. They used just the CAR model, which is a proper. For those who are interested in the details, it's a proper version of the ICAR model. The ICAR model is a limiting case of a CAR model, and this paper here describes that model in this context. So here, what we see is across these districts of South Africa, we see there's two sets of estimates here. These orange estimates of a point estimate and then an interval around them. So we can see some of these are very, very wide. So these are the direct survey-based estimates, not using any other information, just weighted estimates. And then these green estimates are Fay-Herriot from that model I've just described. And we can see, overall, the central location is quite similar, but, there's some cases where we do see more shrinkage. This area here, is highly uncertain, so there is more shrinkage here. But we see these green bars are in general much narrower, which is showing the benefits of this particular model. And this just maps two outcomes, HIV prevalence at the top. So so these are the smooth estimates, and then these are actually people living with HIV. So that's more like a total we were interested in there. Okay, so let's explain this model to a temporal space-time setting, and then we'll look at some more examples. So now we'll let PIT hat be the prevalence estimate the design base, so the weighted estimator in area I and in period T, year T, for example, or a 5-year period. And then again, we're going to take the logit and we're going to model the logit. So the logit has got this known variance, which is from our design-based estimate, is a design-based estimate. And then we're going to decompose this theta IT, this logit of the prevalence, into these different terms. We have an overall intercept, then we have two main effects for time only, so a smooth term in time, and then we have a shocks in time, so random one-off shocks which are unrelated to anything around them. Then similarly we have spatial noise, and then spatially smooth term, SI, and then finally we have this interaction which allows, so that without that term we just have a main effects term, and so now we'll have main effects only, so now we're going to allow interactions so we can deviate from those overall temporal and spatial trends. And this model was discussed in the previous lecture that I gave. So now, before I give some examples, I just want to talk about discrete hazards models, because we're interested in undefined mortality, and so to do that we need to think a little bit about some survival analysis models. So the aim of this work is to try and obtain estimates of undefined mortality in countries which don't have vital registration systems or have limited vital registration systems. And so we're going to try and estimate undefined mortality at a subnational level to aid with policy interventions and assess program targets. And then we're going to use data from these demographic health surveys. If you remember, these are stratified cluster sampling. They have a stratified cluster sampling design, and they collect data on lots of different health and demographic variables. And they've been carried out, there's been hundreds of these surveys carried out in many countries for many years. And so we have this sparsity problem, and so we want to try and do some space-time smoothing. So this is repeating in a little bit more detail what I just said. So we have stratified, so we stratified sampling, so by urban, rural, crossed with some kind of area level. This is actually in the Kenyan DHS. I put 8 regions here, but in general, it's going to be stratified at the admin 1 or the admin 2 level. If you remember, admin 0 is country, admin 1 is one below that, admin 2 is one below that. And then, so all women at age 15 to 49 who slept in the house the night before are interviewed and asked a number of questions, including what's known as their full birth history. So the birth dates of all their children, and then if their children died, when they died. And then the DHS provides the responses along with design weights to reflect the design. And then also GPS coordinates. We're not going to talk about jittering here, but they're actually moved a small amount, or different amounts in urban and rural to protect confidentiality. So we're interested in the survival of a child to age 5, and so we could think about modeling the survival curve for the first 5 years of life either continuously via some parametric distribution such as the Weibull or the gamma, or we could think of discrete models which split the age, the first few years of life into subintervals within which we think there might be very different hazards. So the hazard is the probability of dying given you, in a particular period, given you were alive at the start of that period. And it's a very natural thing to model in a survival context because of dropout. You can just look in every interval and look at how many people you had at the start, then how many died in the subsequent intervals. So it's much more natural to look at the hazard rather than the overall probability of dying, say between month 1 and month 12. It's more natural to look at the probability of dying in between months 1 and 12, given you were alive at the start of that period. So here we're going to, this is quite typical in this, for this kind of this kind of application. The first month of life is very significant, and so many, in many countries, we've examined almost half of the deaths that occur in the first 5 years of life occur in the first month of life, and so we have a specific category for that, and then we look at months 1 through 12, death in that period, and then yearly from that point onwards. So we have 6 different categories. And this just shows what we're, just pictorially, what we're actually doing here. So we're modeling all the data on a monthly scale. So every child that is born and is examined subsequently, we have an indicator, a monthly indicator of whether they are dead or alive. So a child that lives for 60 months, the first 5 years of life, would just have a series of, say, zeros, and then if the child dies at the 37th month, they would have zeros and then a 1 at the 37th month. And so we need to estimate these hazards for each of these for each of these months. And so in demography speak, NQX is the risk of death between months X and X plus N, so in an N-month period, giving you a survived until the start at point X. And then surviving for 5 years, so here this is indexing for area I and time period T, so we're going to fit models to each area and time period we're interested in. So if surviving 5 years, you need to survive all 60 months, so you need to survive each of these months. So this just says you survive to the end of the first month, given you survive to the first month, you survive the second, etc. So the under 5 mortality is just 1 minus that. So 60Q0 is 1 minus the probability of surviving that in that over the whole period. So the way we work this out is, so it turns out that this hazard model, this discrete hazards model, can be written down as a sequence of logistic regression models. So you expand the data to have these zeros and ones, then you fit this model. You need to acknowledge the design. So it's a weighted logistic regression, but not just the simple version of weighted regression where you say you have weights in the conventional statistical sense, excuse me, because that will lead to the wrong variance. But there's a technique which was described in Binder 1983, where you basically weight the score function and then estimate the coefficients, these log odds ratios parameters. So you have 1 log odds ratio for each of the bands, so 6 of those in each of your area and time periods. You estimate these via this weighted score function, and then the appropriate design is found using the techniques that were described in the first lecture. So that's one way of approaching this. So that's what I'm going to be talking about now. That's a design-based approach. There's a model-based approach which I'm not going to talk about in any great detail, but basically you take a product of, you just fit a likelihood with a logistic regression to your data, but you have to include stratification variables and also cluster random variables to random effects to acknowledge the stratification and clustering. So at the moment, we're going to think about this design-based approach. So these methods are all packaged up within the summer package we've talked about. So the summer package makes great use of the survey package in R. That does all the fitting I just described using the survey GLM function. And then the space-time models are fit using INLAR. And this is very, very fast. So this can be done for countries in a very short amount of time. So these are actually weighted 5-year estimates for Ecuador. And so we see from looking at periods between 85 to 89 through to 2010 to 2014. Again, lighter colors are preferable. And we see that the maps are getting lighter as we proceed through time. And we see there's more uncertainty in older time periods. Very interesting aspect of these designs. These are all based on design from a survey from 2013. Because if older mothers, relatively older mothers, so a woman say of 49, she may have had her first child at 16, and so that's telling you something what happened 30-odd years previously. And so you can learn these retrospective birth histories. You can go back in time a long way, but of course you get less births in earlier years, and so there's more uncertainty here. And this black area here is an area we didn't have any data, or we couldn't form a reliable estimate. And these are actually the smooth estimates. So applying that space-time smoothing model I talked about. So just to summarize the steps, we fit those logistic regressions using the survey package. We combine them all together to get a weighted estimate of the under 5 mortality with an associated variance, model the logit of that quantity, decompose the space-time effects, and then apply the smoothing, and then report the results. So you can see these are much flatter because we've smoothed away the aberrations which the model has decided are sampling variability. So we still see, we could look at this on a more finer scale because this is over such a large scale. This is 150 deaths per 1,000 live births. And so we could look at this final map on a different scale to look at fine detail. But here we see we have this one area seems different, seems a higher rate than the other areas. And if you look closely, you can also see that the uncertainty is less. So say here, remember this map. Here we can see that we can compare the hatching. The hatching is denser here than here in the second map because of the added information because of smoothing over space and time. And this just is another summary where here we've mapped. Sorry, we've done line graphs of the estimates over time in each of the areas. So this can allow us to examine areas that stay high, or just another summary. And then we can apply this up at a grander scale. So we've actually done this at the admin 1 level for 35 countries in Africa. So I won't give you details of all the data here, but there are a large number of DHSs we examined. It took around 2.5 hours to do all the calculations here, so it's not too long considering how much data is being analysed and all the fitting that's going on. So I'll show you some results shortly, but one thing to note is that we can't go down to the admin 2 level here because the starting point here is that we have an estimate of we can obtain weighted estimates and appropriate variances. If we get too sparse data in any particular area and time period, then we don't get a good estimate. So we might get 0 deaths, in which case we'll get a 0 estimate. And so we can't actually take the logit of that. And it's going to have maybe an undefined variance. So these variance formulas, they don't behave themselves for very small samples. So doing this at the admin 2 level is not possible because we just don't have the number of surveys, the large enough surveys that we need. So to get around that, we're going to I'll shortly describe a cluster level model. So these are predictions of under-5 mortality for 2015 in the 35 countries we looked at. So you can look at individual countries here and examine the variation. So here's Kenya. Kenya has got relatively, at least on this scale, is relatively flat. Although if we look more closely, you do see subnational variation. Whereas other countries, I think this is Angola, has much more variation. And then this just says we can also, based on these, it's quite flexible. The INLAR technique, you can generate samples from the posterior distributions, which allows you to look at different quantities, such as the percent reduction from 1990 to 2015. So in the Millennium Development Goals, the progress goal was, can we reduce this by 2/3 in every country of the world? And so here we see, so percentage reductions in blue here are good and showing that we reached this goal. And so overall in these African countries we looked at, those goals weren't achieved. But we can look subnationally to see if these goals were achieved. So here in the 8 counties of Kenya, it looks like one area achieved the goal clearly, whereas some others definitely didn't achieve the goal. And this just shows you what the results look like for one. This is for Kenya, so we can see the time trend. So we put in data at the 5-year period to get reliable direct estimates, but we model at the 1-year scale because we want to, because that gives us more fidelity and we can answer questions like 1990 to 2015. And then this final period, we did predictions out. And we can see there's quite a lot of variation between these curves. There's interactions. So this area starts high, the worst area in terms of our model. Then it drops. So here it will be the area of the third poorest rate. And this large hump here is, I haven't talked about HIV corrections, but we also make a correction for bias because of mothers who die because of HIV. So they will not appear in the survey. Their children are more likely to have died. And so by missing those women, it's informative missingness. And so we try to adjust for that using a bias adjustment. And so I haven't talked any more about that, but that's discussed in the Lee et al. Paper, has more details on that. Okay, so the final topic is cluster level modeling. So rather than model at the area level, taking a summary of the clusters within an area, we can actually look at the individual clusters. So suppose we have MI clusters in area I. So these are the clusters from the 3 DHS surveys, the most recent DHS surveys in Kenya. And then within each of those clusters, we get geographical locations, SC, so that's a 2-dimensional point. and that's where we get our data, and then we have M clusters in total over the whole country, which is the sum of the MIs. And so as a concrete example, I'm just going to talk first about spatial models. So let's suppose we're talking about neonatal mortality. So we're looking at how many children died in the first month of life in a particular time period. So YSC is the number of children who died in the first month of life at the cluster C located at SC. And NSC is the denominator, how many kids were born that we sampled that cluster. Now, in general, with health data examined in space and with demographic data as well, we see over-dispersion. So what that means is we see variability which is greater than that suggested by a binomial distribution, which would be the obvious model to start with here is a binomial for the number of counts, for the number of deaths we'd see over a sample of size n. So one way of modeling over-dispersion is to assume that the prevalences in cluster C, so what I'll call QC, assume that's drawn from some probability distribution. So if we did another survey, we would get a different Q. So there's movement from survey to survey because we're sampling maybe different subgroups within those clusters, and so we're seeing deviations. The key idea here is, though, that the QC that we're assuming is explaining the prevalence in this particular sample we take is common to each of the people in that sample, and so that's going to induce some correlation between the responses, the so-called intra-class correlation coefficient. And so the approach I'm going to describe says, let's suppose those Qs arise from a random effects distribution. Now, a common approach is to add a cluster-level normal random variable on the logistic scale, but we're actually going to think about modeling with a beta distribution. So a beta distribution is a two-parameter family on the for a variable between 0 and 1, so it's ideally suited to what we want to do here. The two parameters AC and BC, unfortunately, they don't have a nice interpretation, but we can say that the average of this beta distribution is AC over D, where D is the sum of the two parameters defining the model. So this can be thought of as some kind of scale parameter. So if AC and BC are large, it means that we're going to have quite a narrow distribution. So the variance of QC is given by this binomial form P1 minus P, which is the PC here being the mean, divided by D plus 1. So if D is very large, it means the distribution is quite narrow, and so therefore we've not got much over-dispersion. Whereas if D is very small, it means we've got a large amount of over-dispersion. So this scale parameter D has then, so maybe it's, it doesn't correspond to a variance, but its size does correspond to telling us how much over-dispersion is present. It can also, it turns out the intra-class correlation coefficient is a function of D, and it's a simple function, it's just 1 over D plus 1. So if D is large, then that's as if we've got independent samples. We don't have much correlation in this cluster. So although the model is written down in terms of A and B, we're going to think more in terms of the mean and the scale, because they're more interpretable. So now let's write down the full sampling model. So the full sampling model says we have a binomial model for our count where the binomial prevalence is drawn from a distribution. And then the reason the beta distribution is so convenient is that it combines nicely with the binomial. It's what's known as a conjugate distribution. And so we can average out over the uncertainty in Q. So here I've written this distribution, the prior distribution for the Q, as a function of its mean and its scale. And so if you integrate out, you get what is the so-called beta binomial distribution. So that's a function. So the binomial is a function of two parameters, a sample size and a mean. Now we have a third parameter, which is the scale, which is telling us about the level of over-dispersion. And so the expected value of our random variable, of our count, is just NC times PC, as we would get from a binomial. And then we get the usual binomial variation, but then inflated by this term NC plus D divided by 1 plus D. So for any value of D greater than 0, we're going to get over-dispersion. And so D, looking at D, tells us about how much over-dispersion is going on here. So we haven't thought about the mean, how we're going to model the mean. Well, now we can go back and model the mean as we would do in a binomial distribution. So, for example, we can say the mean for a cluster sampled at location SC has got an intercept. We can put an urban-rural indicator in here, whether this cluster was in an urban or a rural region. That allows us to acknowledge the design. So if urban areas are oversampled, for example, we can account for that, because we saw in the first lecture that I gave that if you didn't acknowledge the stratification, you take a hit in the variance, but more seriously, you take a hit with bias. And then we've got two random effects, an IID random effect for the area within which cluster lot C lies, and then a spatial random effect. So this is the BYM model I talked about in the spatial lecture. And so now all clusters within the same area I receive the same random effects. So it's a discrete spatial model. And this, for those who are interested, it's actually related. There's a model within Rao and Molina's book, which is described as a twofold nested error regression model, which is is analogous to this, but for a continuous variable. So, of course, we want to do modeling we want our target of inference here, we've stated as being area level prevalences. So, to go from the cluster level to the area level, we need to aggregate. Because we have these constant random effects, this is a very appealing aspect of this model. We can just simply take the prevalence for an urban cluster. All urban clusters are assumed to have the same model, and then all rural clusters are assumed to have the same model because of these constant random effects. So all we need to know to get this, the law of total probability says we need to get the prevalence in the area, we need to take the prevalence for urban, multiply the probability of being urban, plus the prevalence for rural, and multiply by the probability of being rural. So that's what this calculation is here is doing. This is the prevalence for urban, prevalence for rural, and we're just weighting them appropriately. The one snag here is that we need to estimate this proportion of the area that's urban. And that's typically not going to be available for the admin 2 areas, so we need to estimate that in some way. Typically in the DHS reports, they do have some information on the number of areas that were sampled in urban, rural areas, and that gives you some way of moving towards getting these admin 2 level proportions, particularly if you can combine that with some kind of population surface which you can threshold. So now that's for a discrete spatial model. The final thing I want to talk about is a cluster level model which includes a continuous spatial model. So now we have this same binomial model, but now we assume that the probability is P. So most of this looks quite similar. Oopsie, there's a typo there. That epsilon C should disappear. So we have a spatial term now, but this spatial term now is assumed to be continuous. In particular, we're going to assume that follows a Gaussian process, which is what nearly all nearly all spatial continuous models are assumed to be of this form. So most of these terms are common to the previous one. We have this epsilon C, which is a nugget effect, and then we have this Gaussian process. I'm not going to talk too much about these, but if you've got large numbers of clusters, you need to make some kind of approximation to this continuous process. And so I'll talk about one particular approach based on stochastic partial differential equations, which has a very nice implementation within R. Before I just give one slide on that, the other snag here is that we need to aggregate up from the point level now to the area level. The way we can do that is just by integrating. So we average the risk surface with respect to population density. So if we do that, we get the average risk in the area. But we need a complete population density surface here. So this is the analog of here. Here we just need the proportion urban-rural because we've assumed the risk is flat within each of those strata. Here we assume the risk is varying, and so we need to average over that risk. And this just gives you a pictorial description of how the SPDE method is working. This figure on the left is the true field, the true continuous field. The picture on the right is the discretization that's carried out by the SPDE. So it takes these basis functions, these pyramids, and then assumes multivariate normal. It assumes this field here can be approximated by a weighted combination of multivariate normals. And so that's all done within INLAR. exploiting Markovian. So it's done in such a way that the basis functions are constructed in such a way that you get sparsity in the precision matrix, which allows you to the computation to be fast. And so just a very quick example of each of these approaches. So what we're doing here is we've got cluster level data from a Nigerian DHS, and so the data here are actually vaccination rates. In Nigeria, there are 774 local government areas. They correspond to admin 2, and so there are quite a few, almost a third of those areas which have no clusters. So if we tried to do weighted estimates, we see this kind of picture. So these are the measles vaccination rates. So we get higher vaccination rates in the south and then lower rates in the north. And so this picture here just shows on the left column, these are results from the BYM, the discrete spatial model. These results on the right are from an SPDE model. Actually, here we're using beta binomial as the sampling model in both cases. It's reassuring here that the smoothing, the discrete and the spatial, the discrete and the continuous spatial models are giving very, very similar point estimates. So that's reassuring. There are more differences in the standard errors, and in general, the BYM2 models, the discrete model is giving us, the BYM2, I should note, the 2 there is acknowledging a particular parameterization that's used within INLAW, which is very convenient and appealing. So, yeah, there are more details on that in the references, in particular the penalized complexity prize I talked about in my second lecture. The paper there, the Simpson paper there, which discusses those prize talks about different parameterizations. But so here we have more uncertainty. That should not necessarily be seen as a bad thing, because it could be that this is the appropriate amount of uncertainty. As I mentioned yesterday, these continuous spatial models are harder to calibrate than the discrete models, so it may be that we're missing some uncertainty here. Okay, so this is just some very simple cartoon of how I went through the steps here of how I think about fitting these models. So if the level of the spatial and temporal level we need is such that we have sufficient samples to use the weighted estimates, and that's great because they're very reliable. So direct estimation or weighted estimation is the same thing in this context. If we can get away with that, then that's wonderful because we have very few assumptions to make then. If you can get a reliable variance estimate, so if you've got unacceptable variability, but you have relatively reliable variance estimates, so if the design variances are reliable, then you can go to the smooth direct estimation. If you don't have reliable variance estimates, as we didn't in that last example, the Nigeria example, then we can go to the cluster level models. So as we go through here, the modeling gets more hazardous because we're having to make more assumptions. Okay, so just finally, so the smooth direct model is very appealing because it builds on the strengths of all the survey sampling methodology. It allows, with these good properties of weighted estimators, allows to use that along with spatial smoothing models in a very simple way. And as we get more and more data, the usual way that Bayes' theorem works, of course, is that as you get more and more data, the likelihood is concentrated on. The likelihood here is the distribution of the weighted estimator. So as we get more and more data in an area, we will focus in on the weighted estimator, which is exactly the behavior we want. Then, if there's insufficient samples to do this, then we need to move towards cluster level models. And then, as I showed, there was both discrete and continuous spatial models we could use. I should note that adjusting for the design via a model-based approach is not a simple procedure, and that's something that's ongoing research. Model checking, of course, is very important for particularly these cluster level models we're fitting, and that's really in its infancy, and there's not really a lot of hard and fast there aren't really an agreed upon set of methods there, or in prevalence mapping in general. In particular, at the cluster level, there are a number of different models that are being developed and currently under development, and so we haven't seen the last word on that at all. And then just finally, these lectures were supported by were given support by Hewlett Foundation and IUSSP, and the work here has been that I presented as not just historical work, but also work that developed in a large group of people I've been working with, and you can see details about them at this website. Okay, thank you.